Hi friends, it's a pleasure being the part of this video, and it's like I'm feeling so happy about it because as much as we try to talk about it, it really fantasizes us every moment, and we are going to have this understanding. Imagine that we have these two greatest scientists of all time, two greatest minds in human history. And these two greatest minds are sitting together, face to face, in the same room. And one of them is Albert Einstein, and the second one is, if I talk about Einstein, whose name has become almost synonymous with the genius, the man who transformed our understanding of space, time, gravity, light, and universe itself. Now, the guy that's facing this man in this room is none other than Neil Bohr. And Neil Bohr was a physicist who laid the foundation of quantum mechanics and introduced a completely new way of thinking about the nature of reality, at very, very small scales. I may call the smallest scales. These were not ordinary scientists. They were basically the giants of human thought. Now, imagine something even more astonishing, and how we can make more astonishing things out of it is that these two extraordinary minds, they fundamentally disagreed about one of the deepest questions ever asked. The point is that how does nature actually work? Does the universe possess a definite reality even when no one is looking, no one is able to observe? Or does reality itself become definite only when measurement is made? Guys, we're going to talk about the debate. And this was not a disagreement over small scientific details. It was a disagreement about the very fabric of existence. As I talked about. And this question actually challenged our ideas about certainty, probability, causality, observation, reality, and even the meaning of the truth. So friends, I welcome you all. Welcome to one of the greatest intellectual battles in the history of science, in the history of science and mathematics. So here I welcome you to the Bohr-Einstein debate. It may not happen in just one video. There may be a couple or more videos which will try to take on this story. All I'm going to do is to talk about the story of this great debate that took between Albert Einstein and Niels Bohr. And today we are not merely going to study the history, we're going to relive one of the most fascinating scientific, I may call it conversation, scientific conversation that has ever been recorded in the field of science. Now, by the end of this one-sided interaction, you will understand why this debate lasted for decades. It was not a one-time debate. Why it continues every day in different forms, and how it transformed modern physics, how it transformed the nature of modern physics forever. Whether you are a student, or you're a teacher, or a researcher, or simply someone fascinated by the mysteries of nature, this journey will change the way. It will change the way you think about the reality itself. It will certainly make an impact on your mind, and your mind will start playing games to understand the reality. So sit back and keep your mind open, and let's begin. Let's begin this argument. Let's begin this conversation that happened over a long period of time. And before we talk about Einstein, the genius, Bohr, the genius, let's ask a very simple question. The very first question: why did this debate arise in first place? I mean, after all, science had already achieved, it had achieved remarkable success by the beginning of the 20th century. It was advancing, and a lot of things had completed in certain frames. And scientists had explained the motion of planets. They had understood gravity, and they had described electricity and magnetism, a complete framework in the form of Maxwell's equations. Steam engines, telegraphs, railways, and electric lighting had already exponentially transformed the civilizations on this planet. And in those times, many physicists believed that almost everything important had already been discovered. This was the feel, this was the scientific feel of the time. And some even thought that physics was nearly complete. The problem was our deficiencies, the problem was our inaccuracies, the problem was the non-availability of the technology. And only a few small details seemed to remain. They seemed to remain unexplained. But I may tell you that history surprises us. Sometimes the greatest revolutions begin with the smallest puzzles that could not be explained. And a few strange experiments started revealing behavior. that no existing theory could explain. They were minute things for these physicists, for these scientists. Light, light behaved in unexpected ways, and atoms, atoms produced mysterious spectral lines, discrete spectral lines. Hot objects, uh, hot objects emitted radiation that classical physics could not correctly predict. They could predict the so-called ultraviolet catastrophe. Electrons seem to occupy only specific energy levels in atoms, in molecules. The microscopic world refused. It completely rejected. It refused to obey the rules that had worked so beautifully for everyday objects, that had worked for planets, that worked for machines, that worked for cars, that worked for airplanes. Now imagine trying to explain the movement of a football. You have a football you want to predict. You can predict where it will go, provided you know the initial conditions, you know the size of the ball. You know that every effect has a cause. So the point is here, if you know the initial conditions of this football, you can calculate the future of this football precisely. You can completely, exactly predict the future of this football. This way of thinking had guided science for centuries. Galileo Galilei, Newton, Einstein. It's called deterministic thinking. You know the initial conditions, you can predict what exactly is going to happen to this ball. But nature appeared to behave like a perfect designed clock. Every gear moved because another gear pushed it. So nothing happened without a definite cause, a complete framework. And this world, we call it the worldview. Now, this worldview had been extraordinarily successful. It was successful, it was acceptable, it could completely describe the falling of an apple. It described the motion of the planets accurately, precisely. You could make predictions about the planets. And it explained tides. And it explained projectiles. And it explained machines. The working of machines, the efficiency of machines, the friction caused in the machines. And scientists naturally assumed that atoms must behave the same way, the way planets behave, the way a machine behaves, the way a projectile behaves. But nature had different plans. The nature had other plans. When scientists looked inside the atom, when they peeped into atom indirectly, the atom certainly began to disappear. Now, what am I trying to tell is that instead of certainty, they encountered wobbles, they encountered probabilities. So this is small probability, probability, large probability, small and small and small. So instead of predictable trajectories of projectiles, they found the wave-like behavior of these atoms, the electrons in these atoms. Now, instead of continuous energy, they discovered the packets of discrete energy levels, discrete packets. So instead of clear answers, they found deep mysteries. And this is where our story truly begins. I would like to break this story in some parts because it cannot happen in just one shot. Now, the 20th century witnessed a scientific revolution, as I already told you, unlike anything before it. And at the center of that revolution stood two remarkable individuals. I'll try to focus my beam on these two persons. One is Albert Einstein and another is Neil Bohr. Both the persons are physicists. And ironically, Einstein played a major role in developing or in creating the postulates of the quantum theory. So for Einstein, so when I talk about Einstein, in 1905, he explained the photoelectric effect by proposing that light sometimes behaves as if it consists of tiny packets of energy. The packets of energy. Now, this bold idea later earned this genius a Nobel Prize. So here is one of the greatest ironies in the science. As I talked about this man, the genius, Einstein, basically he helped build the quantum theory, to build quantum mechanics. But later on, he became one of its strongest critic. Not because he rejected experiments, but because he believed that the theory was incomplete in revealing the nature of reality. Now, the other fellow that I have is the genius Bohr, Neil Bohr. Neil Bohr, meanwhile, accepted that quantum mechanics required a fundamentally new way of thinking. And Bohr, he argued that nature at the very microscopic level simply does not behave according to our day-to-day intuitions. Now, that difference in philosophy, Einstein and Bohr, that difference in philosophy became the heart of Bohr-Einstein debate. This story is all about this debate, but we are trying to build some kind of foundation on this debate. Now, over the next 90 minutes, which I will certainly break into the parts, we will follow this remarkable story. We'll try to go through this one by one, step by step, and we will explore the scientific discoveries that gave birth to quantum mechanics. And in order to build this kind of formal talk, we will revisit the famous Solvay conference where Einstein repeatedly challenged Bohr, repeatedly, with the ingenious thought of with ingenious thought experiments. And we will examine the uncertainty principle, at least in philosophical sense. We'll not go into the mathematical formalism here. And this uncertainty principle has a nature of complementarity, the EPR paradox, and we have this Schrodinger's famous cat. Then we have the Bell's theorem and the experiments that tested these ideas, which were confronted by these two geniuses. Now, most importantly, we will ask the question that has fascinated generations of scientists. And what's that question? That question is, what is reality? And does quantum mechanics provide its complete description? Can quantum mechanics completely describe the nature of reality? That's not merely a lesson nearly a lesson about physics. It's a lesson about how science progresses, how science goes on and on. And great science, I can tell you that great science does not advance because everyone is going to say, yes, boss, you're right, boss, right. Science cannot go this way. This way, science cannot go. It advances because brilliant minds respectfully challenge one another. They have that freedom of challenge, and every objection, every constraint that you drop, it sharpens a theory. It makes the theory more fundamental. It makes theory more clear. And every criticism forces the deeper understanding. So you have disagreements, and every disagreement brings us closer to the truth. We always go close to the truth. We can never know it because of uncertainty. And guys, the Bohr-Einstein debate is perhaps the greatest example of this process that I tried to describe before in all of scientific, in all of science or in all of scientific history. So let's travel. Let's travel back more than 100 years to a time when the foundation of modern physics were about to be shaken forever. Let's go back there. Let's try to dig out. And here our journey begins with the birth of the quantum revolution. And the target is this debate. And the target is the Bohr-Einstein debate. So here I'll take on the first part of it, and then we will move on to the next part, the birth of the quantum mechanics. I will take this as the first part, and this is the birth of quantum revolution. So ladies and gentlemen, now that we have understood why the Bohr-Einstein debate became one of the greatest intellectual confrontation in history. And let's travel back to the late 19th century to describe, or I should say, to appreciate this debate. And for that, we must first understand the world in which it emerged. So this is my first part. Again, I'll go back to make it more interesting. Imagine that you are a physicist and you are living around the year of maybe 1890 to 1900. And physics here, it appears to be an almost complete subject. The laws of motion that were formulated by the Isaac Newton, they successfully explained the movement of the falling objects. Cannonballs, the projectile of the cannonballs, planets, comets, and tides. And then we had James Clerk Maxwell. This man had unified the two independent theories. It unified electricity and magnetism and light into a single elegant theory. And in this time around, we have thermodynamics. And thermodynamics had explained heat and engines, and scientists could predict eclipses, and they could predict these eclipses in advance. Engineers were building bridges and steam engines, electric generators, and communication system based on these theories. And there was an overwhelming feeling in the field of science, overwhelming feeling that the grand structure of the physics was nearly finished. It was done. It was over. It was gone. You could predict everything. And many believed that only a few minor details remained to be solved. As I started this argument, but history teaches us an important lesson. And whenever science appears complete, it seems it's complete, it's over, we have done it. Nature often reveals a deeper mystery. And that is exactly what happened. The first cracks appeared when scientists studied something that seemed very ordinary. And what was that ordinary thing? It was the hot objects, the heated objects, the objects that would emit radiations. When you heat a piece of iron, it first glows. It becomes red, then orange, then yellow, and finally almost white. This change in color, it reflects a change in the light emitted by the objects. And what classical physics does here, the physics that was assumed to be complete, the classical physics predicted how this radiation should behave. But when the experiments were performed with increasing precision, the predictions failed. The predictions did not fail to some degree. The predictions failed dramatically. And the theory suggested that a hot object should emit an infinite amount of energy at a very, very short wavelength. This is a long wavelength, then you have a short wavelength. For short wavelengths, a lot of energy should come. An obviously impossible result. And this contradiction became known as I said, ultraviolet catastrophe. It was not merely a small error in the field of measurements. It was not an error in calculations. It was a sign that the existing framework of physics was missing. It was missing. Something fundamental was missing. And in 1900, the German physicist, everybody knows, maybe not the general public, it was Max Planck. And Max Planck proposed an idea that even he initially regarded as a mathematical trick. He was feeling that he is tricking. And he suggested that the energy is not exchanged continuously. Instead, it is emitted or absorbed in tiny discrete packets, which Max Planck called as quanta. Now, this simple assumption, it matched to the results that were obtained. It matched the experimental data remarkably very well. The data was behaving like this, and Planck had unknowingly opened the door to an entire new chapter in physics, a new framework in physics. And at first, no one realized how revolutionary this idea would become. Even Max Planck himself did not believe that nature was truly quantized in such a profound way. Yet this single idea became what we call as the seed of the tree of quantum mechanics, the seed from which quantum mechanics eventually spread out, grew. Now let's move to the year 1905, often called Einstein's miracle year. People call it miracle year. During this extraordinary year, Albert Einstein published several papers that transformed physics. And one of the papers was explaining the Brownian motion, providing strong evidence that atoms are real. Atoms do exist. Another introduced the special theory of relativity and challenging our understanding of space and time. And then there was the third paper that explained the photoelectric effect. And this paper is especially important for our story, the story that we are going to talk about. Experiments in those times had shown that when you shine light on certain metals, these metals could eject electrons, because in metals the electrons are free, they could cross over these boundaries. And classical wave theory could not explain why the energy of the emitted electron, it depended on the color. The color, I can say, it depends on the frequency of the electromagnetic radiation that's falling on it, the frequency of light, rather than simply it should depend on the intensity of light. Now here Einstein proposed a bold explanation, and everybody knows about these experiments. He suggested that light sometimes behaves as if it consists of the tiny packets of energy. Now each packet carries an energy proportional to its frequency, what we call as E equals h nu. And today we call these packets as photons. And this idea was strange, it was astonishing. It was astonishing because for centuries, scientists had gathered overwhelming evidence that light behaves as a wave. Now, Einstein was saying that under certain conditions, he's using under certain conditions, it also behaves like particles. It also behaves like a collection of particles. Now, how could both be true? And this was the beginning of, we may call it, it was the beginning of the deepest puzzles in all of physics. As more and more experiments were performed, as more and more experiments were conducted, people had similar surprises. Similar surprises emerged. Electrons, which everyone thought were particles, sometimes produced interference patterns, which is a result of the wave nature of light, a characteristic feature of waves, of water waves. And light behaved like a particle in one experiment and like a wave in another experiment. In photoelectric effect, it's behaving like a particle or a group of particles, and in another case, it's behaving like waves. And electrons behave like particles in one experiment and like waves in another experiment. So nature seemed to refuse the simple categories that had guided physics over centuries, for centuries. I can portray it like, imagine watching an actor. You have an actor performing two completely different roles in the same play. At one moment, the actor appears as a king. At another moment, the same actor appears as a humble farmer. Now, if you insisted that the actor could only ever play one role, you would be confused, because quantum objects behave in similarly surprising way of our lives, of the actors, or we are the actors ourselves. And depending on how we investigate them, and they reveal different aspects of their nature. And this strange behavior, it certainly forced physicists to ask a profound question. Is the problem with the nature, or is the problem with our classical way of thinking? As the evidences that the science has, as the evidences are accumulated, it became increasingly clear that the microscopic world obeys the rules that are different from those governing everyday experiments. Building a car, building a machine, launching a rocket into space. This realization prepared the stage for new generation of physicists. And among them was a young Danish scientist named Niels Bohr. We may also call him Niels Bohr. And Bohr recognized that atom itself required a new description. And according to the classical laws, according to classical physics, electrons orbiting the nucleus should continuously lose energy because it's a charge, it's an accelerating charge, and accelerating charge means it should continuously radiate energy. It should lose the speed and spiral into the nucleus in a tiny fraction of a second. Now, if that were true, stable atoms and therefore stable matter, which is a reality of us, could not exist. Yet the world around us, it is stable. And Bohr proposed that electrons they're allowed to occupy only certain specific energy levels, while remaining in one of these allowed orbits. They do a miracle, they don't radiate. They don't follow that electromagnetic laws of electromagnetic radiation. Only when electrons jump from one energy level to another energy level, it emits or absorbs the light. It emits or absorbs the light photons with precisely defined energies. Now, this bold idea successfully explained, it could purely explain the spectrum of the simplest of atoms. What we have is hydrogen atom, and marked another milestone in the development of quantum theory. It was not the final answer, but it demonstrated that classical intuition alone could no longer no longer explain atomic phenomena. The scientific community had entered an unfamiliar territory. The old picture that seemed complete, that the old picture of nature as a perfect, predictable machine was beginning to crumble. It was crumbling. A new picture, strange, probabilistic, and deeply counterintuitive, was slowly taking a shape. And at the center of this, emerging revolution, stood these two remarkable thinkers. Here, I think, was Einstein, and here was Bohr. One was willing to accept the nature, it was willing to accept that the nature itself is fundamentally different from human intuition. The other believed that the theory, despite its extraordinary success, it was still incomplete.